what we're going to take a look at, this is problem number 2, or I'm sorry, 3. Ashley swimming across a river. One of the first things you're going to need to get in the habit of doing when we're dealing with vectors is make sure you understand what I call the coordinate system. Make sure you understand what's positive and what's negative. Positive x, negative x, positive y, negative y. And for the most part, we're going to follow the basic convention that we're going to just use the basic right-hand coordinate system. To the right is positive x, to the left is negative x. Straight down is negative y, straight up is positive y, and this works pretty well with just simply north, south, east, and west. And so on these problems where I designate the direction west, that's actually negative x. North will be positive y. So that, and we should get in the habit of doing this because then it makes sure all the vectors are set up properly. Ashley can swim 3 meters per second in still water. Okay, that tells us how fast she can go, but not where she's going. While trying to swim directly across the river, she is pulled by a current flowing south at 2 meters per second. So the river is going south at 2 meters per second. She swims east, and she can swim at 3 meters per second. So these are the two vectors we're going to add up. I don't have them drawn head to tail. It doesn't matter. If you want to, you can redraw them. Okay, 3 meters per second, 2 meters per second. That's the resulting velocity. That's what we want to calculate. If you want to do that, that's fine. You don't need to. Because the diagram that you drew basically shows you how the vectors are set up. Because then you're going to put this information into a table. And the table consists of what is the vector? One vector is Ashley. And it's broken down into x and y. This table you will see on every vector problem. I always do it. What is the component of Ashley's vector in the x direction? 3. Positive or negative? Positive. It's going in the positive x direction. Is she, hold on, just a minute, is she going any place? Is she intended? Because she is swimming directly east. Is she doing anything up or down? No, so it's 0. Now the current will end up pushing her down, but we don't account for that in her initial vector. Okay, now the current, the vector for the current, is it going any place in the x direction? No. What is the direction of the current? Straight down, which gives us a negative 2 meters per second. So we broke Ashley and the current up into its two x and y components. And now we add it together. And so our resultant velocity is going to be 3 in the positive x, and it's going to be minus 2 in the y. This defines what our resultant velocity looks like. 3 in the x, 2 going down. There's our resultant velocity. The hypotenuse, that length, is what we want to calculate. And how do we calculate it with this information from the x and y's? Pythagoras tells us how to do it. You know, square 3, square minus 2, that's 13. You take the square root, that's square root of 13, 3.6 meters per second for this problem. Are we done? No, because if I ask if we're done, chances are we're not. Why aren't we done? The what? The angle. It asks, the problem wants the resultant velocity. Velocity has magnitude. We know the magnitude. The magnitude is 3.6 meters per second. We got that right there. We need to know the angle. Yes, so we want the angle. And there's been some good questions earlier today. How do I know which? We have three choices of the angle in the triangle. Which one do we want? Well, she starts swimming that direction, but the current is pushing her down. So the angle we're interested in is this one right there. That's the angle we got to calculate. So I call that theta. Sines, cosines, tangents, whatever you want to use. If you have all three sides of the triangle, you can calculate anything you want. Yes, ma'am. Do you want to do sines or cosines? Cosine? Okay. For some reason, I'm kind of partial to cosine myself. Now, do you want me to write it all out nice and long? Okay, that's fine because we haven't done this that much. Basically, we want the cosine of theta. That's the angle theta. Cosine is adjacent, 3, over the hypotenuse, 3.6. And that gives us, when we do the math, 0.833. The cosine of some angle is 0.833. I've done it 4 times today. The cosine of some angle is 0.833. We want to know what the some angle is. When we go from angle to number, we use cosine. When we go from number to angle, we use the inverse cosine function, which is a shift cosine. And that's written with a cosine with a -1. We want cosine, the inverse cosine of 0.833. That takes us from a number to an angle. It's the opposite of a cosine. And you have the same thing for sine. You have the same thing for tangent. All those trig functions have inverses. And when you take 0.833, the inverse cosine, you get 33.6 degrees. You get a nice angle. You want to take the inverse cosine of 3 over 3.6. Okay? Because we ultimately want the inverse cosine of 0.833. Or the inverse cosine of 3. And you can punch it into your calculator like this. That's fine. And when you do that, do you see you'll get the right answer. Do you see what I'm talking about? Do you see why? More importantly is not you get the right. Yeah.